There are two laws in physics that look extremely similar. We have Newton's law of universal gravitation, which describes the attraction between two objects due to gravity. And then we have Coulomb's law, which describes the attractions of two charged particles due to the electrostatic force. They don't only look similar in their magnitude form, but also in their vector form. The electrostatic force between two charged particles will be repelling if both charges have the same sign. Therefore, we have the unit vector here that is pointing towards the charge the force is acting on. With gravity, we will always have attraction with two positive masses. Therefore, the unit vector here has to point away from the object the force is acting on. Well, the first question is, did Newton and Coulomb actually compare notes here and one copy from the other? And the second question is, can we use this similarity to our advantage? For the second one, it's a definite yes. We can use this to our advantage. So how can we use this? So think back a bit when you learned about gravity. I'm pretty sure the universal law of gravity in this form was not the way you learned about gravity first. I'm convinced that somewhere in high school you had learned to calculate the force of gravity as mass times g, and you have remembered that g is 9.8 meters per second square or newtons per kilogram if we're on the surface of planet Earth. Now both laws obviously describe the same thing. So the g here is just a placeholder for all the things in the universal law that is not the mass of the object the force is acting on. So the small g actually is the capital G, the gravitational constant, times the mass of the planet we're on, in this case Earth, divided by the radius of the Earth squared if you're on the surface, and then the vector that points away from the object the force is acting on towards the bigger object that causes the force, in this case the Earth. G is actually a vector field, the gravitational vector field. At any point in space, it has a magnitude and a direction. It always points towards the center of the Earth, so depending on which side of the Earth you are, the direction of the vector might have changed. The magnitude depends on the distance from the center of the Earth. We usually use g on the surface of the planet, but we could calculate g 200 kilometers above the surface of the planet, 300 above, 400 above, and for each location we get a different magnitude. Now we want to use this information to create us a similar shortcut for the electrostatic force. So for gravity, we have replaced the universal law of gravity by the short version, mass times g vector. And now we want to do the same thing. So instead of the mass of the object the force is acting on, we simply take the charge the force is acting on, and we multiply it by, let's call it capital E. Capital E is a vector that, similar to the g vector, replaces everything in the previous equation that is not the charge of the particle the force is acting on. And similar to g, we get a vector field. Instead of the gravitational field, we now get the electric field. Similar to the gravitational field, the electric field will point towards a point charge if that point charge is negatively charged, and the electric field will point away from a point charge if that one is positively charged. Therefore, the field lines that describe the direction of the E vector will always point away from positive charges and towards negative charges. If we look at this equation, it is obvious what the unit of the electric field has to be. It has to be Newton per coulombs. So once I have my electric field, I can simply multiply it by any charge that I put in the field, and I can immediately calculate my electrostatic force on that particle. The same as with g, I could simply take any mass that I want to calculate the force of gravity on and multiply it by the g vector.